So, good day to everyone. Today we will discuss basic principles of DC machines, and also we will try to understand where is the difference between DC motor and DC generator. On this test bench, on this small test bench, we have, first of all, this DC machine which is under test. How do I know that this is a DC machine? So if I will open this cover, then I will see that inside, here's the light, I will see that inside we have a collector, these small plates. I can also rotate them, small plates, I can rotate. So this is the DC machine, Actually, we don't know anything more because we are not able to say is it a motor or is it a generator. Actually, there are no difference. This machine can act like a motor and can act like a generator. But first of all, let's take some description of this test bench. So this is our device under test, our small DC machine. This is the similar DC machine, but it's not under test. It is used to provide braking torque to this machine. So here is the shaft of this machine, and the shaft is mated with this machine. This machine can deflect. From opposite side we have this mesh, and this mesh has some arm with respect to the center of rotation. So it calls some torque when it deflects from the vertical position. This torque can be measured from this scale. It is expressed in Newton meters. So the maximum torque which can be possible to get from here is about 0.1 Newton meter. So if this machine will rotate in the same way, in the same direction like our DC machine, then it will accelerate our machine which is under test. However, if this machine, braking machine, will tend to rotate in the opposite direction with respect to our machine, then this will cause brake. I can switch between these modes, so I can brake, it will tend to rotate in opposite direction, or I can also add some speed to this motor. Now it is in neutral position. This multimeter will help us to see speed. 1 volt, it is 1000 RPM. Actually, it is connected to the voltmeter, but I suppose that it will be better to read from here. And this amperometer will show us current which is consumed by our DC machine which is under test. Current which flows through the brake is not shown here. This rheostat helped me to control this machine, which can add or subtract. So I can add or subtract more, or I can add or subtract less. So first of all, let's take some basics in order to understand what is happening there. So as you probably know, if we will put a wire into the magnetic field, so this is the magnetic field B, and the magnetic field in my case is created by means of permanent magnets. So if we will put a wire into the magnetic field, and if we will do nothing, then nothing will happen. So let's suppose that I would like to get a motor. In this case, I have to supply electrical power into the motor in order to get mechanical power. So I will take this battery, here is the positive and here is the negative, and I will connect wire, one from this side and then another one from that side. In this case, current will start to flow from the plus through the wire and to the minus. Yeah. So this situation is shown here. Circuit now is closed, so we got current. So this current flows from the battery into the wire, then through the wire and back to the battery. So we got wire with current which is in magnetic field. Therefore, ampere force will rise up. Ampere force, as you probably know, is defined like a BLI, yeah, where is this is the magnetic field, this is the length of the wire, or how many turns we have, yeah, in a real electrical machine, and this is the how much current we have inside in the wire. So again, if current flows through the wire, then force, or it's better to say torque, will rise up. So look, if I will apply power, then torque is rising up, yeah? It tends to rotate. Current can be seen from here, yeah? I apply voltage and the current now is flowing through the motor, and therefore motor starts to produce torque and tends to rotate. Okay, now let's suppose that this torque is sufficient to start the rotation. What will happen next? If rotation occurs, then it means that this wire starts to move inside in the magnetic field. However, we know that if the piece of wire is moving in the magnetic field, then EMF is rising up. So now let's see. Ampere force is defined by the left hand. Therefore, the direction will be like this if current flow is like this, and if the magnetic flux strength lines are like this. Yeah. The direction of EMF is defined by the right hand law. So it is versed in an opposite direction with respect to the current. Well, this is really interesting. Look, if we have no motion, then current which flows through this piece of wire is defined by the supply voltage divided by the resistance. This is the Ohm law, yeah? So supply voltage comes from the battery, but resistance comes from this piece of wire. Typically, this piece of wire, this is the armature winding of the rotor. So current is defined by the supply voltage and resistance of the armature, which is really very low. When wire or armature winding starts to move, the EMF is rising up. However, as you can see, this EMF is connected in series with the supply EMF, with the battery, but their directions are not on the same. These are not on the same way, yeah, on the same direction. Therefore, these will subtract from each other, yeah. In this case, so when the wire starts to move, in this case, the EMF will rise up. Therefore, here is the minus, and therefore, once wire is accelerated, once rotation is increased, then this will subtract more, and then current will drop. Why? Because EMF is defined by the equation BLV, where the V, this is the speed of rotation, or speed of motion, V. Let's see. So, I apply the voltage, yeah, and now rotor is immovable. I hold them. Current is here. Now I will release this rotor, and it will start to move. So the EMF will rise up, and therefore current must drop. Yeah? So it stopped, now it is moving. Stopped, moving. So that's how these EMF help us to reduce current which flows through the motor. Very good. So now let's see how do we are able to create motor from this DC electrical machine? In order to make a motor from this machine, we have to supply power. The power is supplied through these two wires, to the armature, and through these two wires to the field winding. So I will set the voltage to the maximum, and the maximum for this motor is 28 volts. And I will switch voltage on. If you will take a look onto the amperometer, initially during acceleration, current will be very high, and then it will drop when the motor will accelerate. Okay, now motor is accelerating. As you can see, we got almost zero torque, almost zero but not zero. This is because if I will disable power, you will see. This is the zero, But now, due to friction in the ball bearings in the brake, we got some small torque, but this small torque is also noticeable. Okay. So, exactly right now, we got braking torque of less than 0.01 Newton meter, and the speed is 5,800. So, let's apply rated torque. Rated torque will be when the current will be rated. Rated current is 2.5 amperes. So look. Brake. I will add brake. I will add brake. More and more torque. And when I add the brake, you can see that armature current increases too. It's fully logical because I start to consume more mechanically from the motor, and therefore motor starts to consume more from the supply network. So let's set by means of brake, let's set current to the rated value of 2.5 amperes. Okay, 2.5 amperes. So we got 2.5 amperes at the torque of 0.06. So we applied 0.06 Newton meters torque, so the motor consumes 2.5 amperes. What about the speed? The speed is 4,600. Okay. Now let's reduce load torque by means of rest. Well, let's say 0.03. So at the half torque, motor consumes 1.4 amperes, and the speed is 5,300. So we take less from the motor, we take less, this is the torque, we take less, therefore motor slightly accelerates. Let's reduce torque even more. As you can hear, speed increases, but the consumed current reduces. As you can see, I'm not able to go exactly on zero because of friction in the ball bearings. Therefore, I have to. Now the brake is switched off, and I have to add slight torque. Okay. So now I can add. Okay, exactly zero. Exactly zero. So at the zero torque, motor consumes 0.4 amperes, and its speed is 6,000. What a joke. Where is the joke? The joke is that we are now working at no load. We do not consume anything, so we are at no load. However, we are still consuming some electrical power. 0.4 times 27 volts. Yeah. So we consume something about 15 watts, maybe 12 watts. Yeah. Why do we consume some power? This current, this small current, and also this small power is used to compensate drags in the ball bearings, because motor is rotating and therefore ball bearings create some braking torque. Very small, but still existing, and we have to overcome this. Now, let's add some torque. I have switched brake into the motor mold. Yeah. Let's add some torque, and let's look what will happen with the current. So I start to add. Yeah, I start to add something. And as you can see, current reduces. Okay. And now it is exactly 0. Somewhere there, yeah. 0. 0 means that our motor under stress do not consume anything. So current now is 0. But in order to make it not consuming anything, we had to compensate torque, which is caused by the ball bearings, by the ball bearing friction. And we know this torque. It is 0.01 Newton meter. So now we have added 0.01 Newton meter. So this was subtracted because it was the brake. And here we add the torque. What about speed? Speed is 6,000.5. So this mode actually is not possible in real life because we are not able to accelerate our motor by means of some additional drive. Yeah? But this mode is called idle. When motor consumes nothing. And this is the no load or real idle. When motor produces nothing but still consumes to overcome drag which is inside in the motor. What will happen if I will add more torque? Let's say I will add 0.02. So I will start to add. And what we can see here, the current direction now goes into opposite direction. Yeah, unfortunately here is the lock. Yeah, we are not able to see that the pointer goes into the negative values. Yeah, again, add less, add more. Yeah, so current becomes negative. It means that we start to supply current back into our supply network. So current becomes negative. How much? Unfortunately, I don't know because I can see it from here. Oh, let's say minus 0.2 or 0.1. Yeah. Because the speed now is much more higher than it was in the motor mode. What about torque? Torque which is added right now is 0.015. Very great. So now, let's analyze what we got. Here, we consume current. It is with plus. We consume current from the power supply network, and we produce mechanical torque, mechanical power. So this mold is a motor mold. We produce mechanical power. Mechanical power, this is the mechanical, yeah. This is the torque times speed of rotation, yeah. And now we start to add torque, so we consume mechanical power, not produce, we consume mechanical power. But current starts to flow outside from the motor, and therefore this is the generator. Here we start to produce electrical power, which is the voltage times current. But we consume mechanical power. So, as you can see, there is no difference between motor and generator. Everything depends on how you will use it. Yeah? If you will rotate this machine, if you will add speed, yeah? If you will rotate this machine, it will produce electrical power. However, if you will supply electrical power to this machine, then this machine will rotate drive, and therefore this will be motor, in a motor mode, and not in a generator mode. Yeah? Once again, brake to 0, enabling, brake, overload, because 2.5 is the maximum, reducing brake. We have still some brake because the resistance of the rheostat is not infinitely high, so I will switch it off. This small torque, this is the ball bearing torque of the brake. Now let's add. Now I start to add. I start to add and current reduces. Back to the motor mode. That's it? Easily, isn't it? Okay. So, if I will show on the graph how it looks like, then you will see that when we increase torque, yeah, then we consume more current. But at the zero torque, we still consume some current. At higher torque, in our case 2.5, we consume much more. In our case 0.06, I'm sorry. Yeah, 0.06. We consume much more, 2.5. And if we start to add torque, then we can consume nothing. So if we will add torque of 0.01, then we will consume nothing, 0, yeah. And if we will start to add more, then we start to produce current. So the direction is changed, yeah. Was plus and now it is minus. So this is the generator mode, and this is the motor mode. With respect to the speed, everything is fully similar. Yeah. If the motor or if the DC machine is rotating slower than its real idle, 6000 RPMs, let's say here. If it rotates slower, then it is in the motor mode. 4.6 we got at 0.06, yeah, and this is the in the idle. So at the real idle, the speed should to be 6.5. 6.5 thousand. And in the generator mode, speed should to be much higher. Here's the results. So now, bye bye.